Section 4.1 of the oceanography course, wave motion. So this is revision for what we covered back in January, I think. So here we have a ship. It's in some pretty bad weather. You can see how big that wave is. It looks like it's about 30 or 40 feet high. That's pretty scary stuff. The motion is pretty violent. The energy transmitted by the wave is about proportional to the square of the wave height. Anyway, so we're going to learn a little bit about how waves move and how they behave. Next topic, 4.2, will be about how they are formed. So the simplest waves are ripples. These are the ones that sort of match your physics textbooks and your maths reasonably well. They're technically called capillary waves because their restoring force is dominated by surface tension between the water molecules. So when a surface is displaced downwards, say by a finger or by the wind pushing it slightly, pressure of the wind pushing the water, surface tension is trying to restore it back to the original shape. So if you just displace it with your finger, you'll see the ripples spread out like so, and then quickly dissipate. If they're continuously formed by the wind, you'll see them continuously move. The shape is almost perfectly sinusoidal, just like a maths textbook has. The wavelength is the distance between the two successive crests. Now with most ripples, that's usually only a few centimetres. And the wave height's only ever going to exceed about half an inch to 3/4 of an inch before it changes its mode. Wave height, unlike physics textbooks, is from the trough to the crest. Now the water itself hardly actually moves. It sort of just displaced up and down, although it does have a slight circular motion to it, where the top is going this way and then it's pulled back by surface tension on the side. Okay, so these are ripples. Key terms of all waves. In oceanography, we tend to focus purely on wavelength and period. We'll also talk about, mention frequency for completion. The wavelength is the distance between the two successive crests of the wave. And this wavelength may vary from a few centimetres to several kilometres. Or in terms of the wavelength of tides, it's like half the circumference of the planet. Symbol for wavelength is either the physics symbol lambda, which is that upside down Y shape, or L, which is used by the oceanography textbook. The period is the time interval between two successive waves. So this might only be a few seconds, or it could be almost up to a minute. It could be, in terms of the longest period of waves with tides, 12 hours. So if you're swimming off Horseshoe Bay, as you go up on the top of a wave, you started a stop clock, and then you went back down, and then you went back up again and stopped the stop clock. That time interval is a period. Okay? It's a repetitive time interval. The frequency is a measure of how many waves occur in a certain time interval. In physics, we usually use per second, but most people on the water, it's about how many times something happens per minute. This is a more suitable unit of measurement. So, for example, you might be at a ship at sea and you get hit by, say, 12 waves every minute. Okay, so that gives you, if the waves hit you, let's say 15 waves per minute, there's a higher frequency. Okay, so that's the frequency is a standard term used in anything to explain the rate of something. So if the wind gets to a certain amount and the waves the height starts to exceed a certain point, so for 3/4 of an inch or so, the wave starts, wave starts to change shape. It moves away from being sinusoidal to developing a sort of more pointed shape, like an angle like this. So it's moving away from this and going more like that. And the reason for this is because gravity starts to take much more of a dominant role over the restoring force. Now, the rolling motion of the top, if you look at the red circle in the animation here, that sort of tapers down. So there's about 5 overlapping circles. It's hard to truly define, but it gets to about half the wavelength. So half the wavelength from here down. Okay, there's still detectable motion where my cursor is, underneath this little red circle. And it slowly peters away. By the time you get down to the bottom of my animation, those points are hardly moving at all. And so we sort of cut it off at half wavelength. Like I say, it's a tapering thing, so it's not entirely sure where it finishes, but half wavelength is a good one. Now, a couple of things about this. If the height of the wave exceeds 7 wavelengths, then the top of the wave starts to break, and you get a foamy crest forming as the air gets into the water. And so it turns just like a foamy white colour. These are called white caps. Usually, as long as the water itself is not moving, that happens when the wind speed's about 12 knots. So white caps start to form around about 12 knots of wind speed. Now we've got 2 definitions here. Shallow water waves are waves that are where the sea depth is less than or equal to half the wavelength. So if we have a line across here, then the rolling motion of the water is interfering with the bottom. So then you've got friction happening at the bottom, which affects the speed of the wave. Okay. Deep water waves is where the water is deep enough that there's no appreciable wave action at all on the seabed. So the seabed has no bearing on the surface motion of the water. So this is another slide to indicate that point. Here, this is our half wavelength point. Okay. And here, the long wavelengths. This is like an ocean swell, so it's got a nice regular pattern to it. Okay, it's lost its energy at the top. So this is long, slow ocean swell. Well, slow is in long period, but it's moving fast. And it's not interfering with the bottom. But as it starts to get close to the bottom, these waves now interfere with the bottom and you're getting friction happening. And that slows down the wave. But the water's still, you still got the same volume of water, so the wave starts to change shape. It gets steeper and the wavelength gets shorter. So the wavelength here is decreasing as it's getting to the shore, and if that exceeds 1/7 of the wavelength, then it's going to break. Now the waves have a lot more effect than wind. And that's purely a factor of the density of water is over 1,000 times more than the density of air. So the speed of the waves. So these are the speed, how fast the wave motion travels across the surface of the ocean. And we've got 2 definite boundaries. Shallow water waves, it's very dominated by the depth of the water. The shallower the water is, the slower the wave is going to go. And there's a little equation there. V equals the square root of G times the depth. That's the depth in meters, and that's the speed in meters per second. And G, if you can remember from physics, is 9.81 meters per second squared. So this is what we see happening on beaches like Shirley Bay and Horseshoe Bay and things like that. Deep water waves, the speed of the wave is dominated by the wavelength. And this is a simplified equation. The speed is 1.25 times the square root of the wavelength in meters. And this is why ocean swells happen. We have, for example, You can have no wind off St. David's, yet you can still have an ocean swell running, usually without breakers. They're just sort of like this. Now they'll break when they come to the beach, but the water's more almost sinusoidal. Now the wave is actually moving pretty fast, and it was created by a storm, sometimes hundreds and hundreds of miles away. But because those long wavelengths move faster than the shorter wavelength ones, these swells are getting to us long before anything else does. So we can often get swell off Bermuda even if there's no wind at all to generate local waves. Swells, it's kind of cool if you want to go surfing or swimming, and it's nice to mess around on the beach. It can make you pretty seasick if you're offshore. So these couple of photos, not mine, found on the internet somewhere. So the photo on the left is there's no wind. You can see those two fitted dinghies are hardly moving at all. But it's the surface of the water that's interesting. There's hardly any ripples at all, except there's a patch just sort of underneath the lighthouse between the dinghies. There's a patch where there's slightly more ripples, and that indicates there's slightly more wind. So sailors in light wind conditions will be looking for these dark patches of extra ripples in the water. And there's a few extra ripples behind one of the dinghies to show that, you know, there's a boat is pushing the water away and creating the ripples. On the right hand image, you've got a humpback whale breaching off South Shore. Rather spectacular photo. This kind of the whale is pretty cool, but I'm more interested in this case of the water itself. You see the texture of the water is totally different from the image on the left. Okay. The waves are much more angular, the waves are higher, you've got white caps are forming. So looking at the shape of these waves, sort of numbers of white caps and the sort of height of the waves, I judge the wind speed to be about 15 to 20 knots. Okay. And you know, the motion of you on a boat would be a lot more violent than this calm situation on the left. So as always, there's more information and links for you. I put links to videos that have been done by some sort of smart people on YouTube. So that's all on the section 4.1 of Island Physics website. So go from that. Remember, that is kind of like your go-to area for material for studying for your exam. I'm going to try not to ask anything on your exam that isn't, you know, on the website or in your class notes or in videos such as these. And there's also the textbook, obviously, from page 296 onwards. It can get quite technical and gets quite into depth. And lastly, if you are lucky enough to be locked down in a house where you can see the ocean, see the water, try and look out at the water and look at see if you can estimate the wavelengths, the wave heights, see the different shapes of the water. So when it's light winds, you see the water more sinusoidal shaped. When it's stronger winds, you can see the more angular shape. If it's winds above 12 knots, you'll see the top of the wave breaking off to form a foamy white head, okay, white cap. If the white caps get particularly exciting and big, they tend to get called white horses, because it sounds cooler. Okay, we'll put a stop there. Make sure you do some reading up on that and watch some of those videos. And then next lesson, we're going to talk about wave formation.